Hi folks, we're moving on to Unit 2 in our look at the Advanced Higher Physics past papers. And the first thing in Unit 2 we're going to have a look at is an introduction to quantum mechanics. And if you click on Advanced Higher Past Papers on the Calder High School website, you'll see that there's a link there to past papers sorted by key area, thanks to Mr. Davey. And we're going to use that to select a couple of questions on an introduction to quantum theory. And in this video we're going to have a look at the 2019 paper and the 2022 paper. So firstly, 2019 paper, and as usual the first thing you'll see is the data sheet. And in these questions the sort of thing you might need is Planck's constant, or the mass or charge of some subatomic particles. We're going to start off by having a look at question 8, and you might want to have a go at the question yourself first and then come back and see how we have gone about it. So, muons are created when cosmic rays enter the atmosphere of the Earth, and this is shown in figure 8a, and to an observer on the Earth the muons appear to have a lifetime of 8.5 microseconds. And instruments on the Earth can detect muons and measure the muon energy E. And the precision of the muon energy measurement is limited by the lifetime delta T of the muon. And by considering the Heisenberg uncertainty principle, calculate the minimum uncertainty in the muon energy delta E min. Well, straight to your relationship sheet here, and we're going to write down the version of the Heisenberg uncertainty principle that has energy and lifetime in it. So delta E, delta T is greater than or equal to h over 4 pi. And if it's the minimum uncertainty in the muon energy delta E min that we're looking for, then delta E min times the lifetime, 8.5 times 10 to the minus 6, will be equal to h over 4 pi. You can only change the inequality sign into an equal sign when you specify that it's delta E min that you're looking for, and substitute in the lifetime. And then if you do that on your calculator, you'll get 6.63 times 10 to the minus 34 over 4 pi times 8.5 times 10 to the minus 6. And that gives you an answer of 6.2 times 10 to the minus 30 joules. And make sure you state that that's delta E min. Okay, part B. Some muons detected at sea level have an average energy of 4.1 times 10 to the 9 eV, that's electron volts, and an instrument detects 10,000 such muons in a minute, and we've to determine the average total energy in joules measured per second. Well, first thing we need to do here is convert the 4.1 times 10 to the 9 eV into joules. And all you have to do to convert electron volts into joules is multiply by the charge on the electron. So 4.1 times 10 to the 9 times 1.6 times 10 to the minus 19 gives you 6.56 times 10 to the minus 10 joules. That's the muon energy in joules. And there's 10,000 of them in 1 minute. So if we multiply that by 10,000 and then divide by 60, then we will get the average total energy in joules measured per second. And that's 1.1 times 10 to the minus 7 joules. Okay, part C. At sea level, these muons have an average momentum of 4.87 times 10 to the minus 19 kilogram meters per second. By calculating the de Broglie wavelength of a muon with this momentum, explain why muons at sea level can be regarded as particles. So if we need to calculate the de Broglie wavelength, that's the relationship we use. That'll be 6.63 times 10 to the minus 34, that's Planck's constant, divided by the momentum, and we're told that's 4.87 times 10 to the minus 19. You do that in your calculator, you'll get 1.36 times 10 to the minus 15 metres. And by looking at the magnitude of that wavelength, then the wavelength of the muon is too small for any wave-like behaviour or any interference effects to be observed. So the muon can be considered to be a particle. Let's have a look at the marking instructions. And in fact, here's a good wee tip for you. If you use Mr. Davies' past papers by key area, and you click on the question that we're looking at, it's question 8, and you scroll right to the end of that, then the marking instructions are tagged on the end of the question, so no need to go looking for the separate marking instructions. They're there, and that matches what we have done. All looks good. That was the 2019 paper then. Let's have a look at another one. This time it's the 2022 paper. Same key area, introduction to quantum mechanics, and we're going to have a look firstly at question 6. And again, it's the Heisenberg uncertainty principle. So there's the Heisenberg uncertainty principle relationship, or at least that's the one that has position and momentum in it. And we have to state an implication of this relationship for a quantum particle. Well, straight from the specification document then, this relationship implies that the precise position and momentum of a quantum particle cannot be known simultaneously. Make sure you say precise there, and also simultaneously. Okay, part B. An alpha particle is emitted from a uranium-235 nucleus, and according to classical physics, the alpha particle cannot overcome the strong nuclear force holding it in place in the nucleus. Explain in terms of the Heisenberg uncertainty principle why alpha emission is possible from a uranium-235 nucleus. Well, there's my little uranium-235 nucleus there, and an alpha particle coming out from it. That's the sort of diagram you might have seen in National 5 physics. Now, according to classical physics, that shouldn't happen. But if we look at the version of the Heisenberg uncertainty principle that's got energy and lifetime in it, then if the lifetime of the alpha particle is short enough, then the uncertainty and the energy can be large enough that the alpha particle can have sufficient energy to be in a location where, according to classical physics, it doesn't have enough energy to be. So it can have enough energy to occupy a position outside of the nucleus, and therefore it can be ejected from the location of the nucleus. Let's have a wee look at the marking instructions. So 6a, the Heisenberg uncertainty principle. It's not possible to know the precise momentum and position of a quantum particle simultaneously. And on the right hand side there, you could also have answered that in terms of energy and lifetime. And then part B, the explanation of how alpha decay can happen. Well, the left hand side of the marking instructions is answering it in terms of position and momentum. So if the momentum of the alpha particle is known precisely, then its position is not known precisely. So there's a small probability that the particle could exist outside the nucleus, even though classically it doesn't have sufficient energy to escape. We answered it using the right hand side of the marking instructions there, stating that if the lifetime is known precisely, then its energy is not known precisely, so there's a small probability that it's got enough energy to escape from the nucleus, even though classically it doesn't have sufficient energy to do that. That's pretty tricky. Alright, moving on, 6 part C. The mean lifetime of an alpha particle within a uranium-235 nucleus is 0.7 microseconds, and we have to determine the minimum uncertainty in the energy of the alpha particle. So again, we're going to use the version of the Heisenberg uncertainty principle that has energy and lifetime in it. So delta E, delta T is greater than or equal to h over 4 pi. And therefore delta E min is what we are looking for, the minimum uncertainty in the energy. And as soon as we express it as delta E min, we can then change the greater than or equal to sign to an equal sign. And that will be equal to Planck's constant, 6.63 times 10 to the minus 34, divided by 4 pi times the lifetime that we're told in the question, which is 0.7 microseconds. That's 0.7 times 10 to the minus 6. And if you do that on your calculator, you'll get an answer for the minimum uncertainty and the energy of 7.5 times 10 to the minus 29 joules. Let's have a look at the MIs. Remember, if you're writing the relationship from the relationship sheet, it must have the greater than or equal to sign in it. But as soon as you state delta E min is what you're looking for, then you can reduce that to an equal sign. Alright, let's move on and let's stick with the same paper, because question 7 in the 2022 paper was an open-ended question on an introduction to quantum mechanics. So let's have a wee look at this one here. It's a use your knowledge of physics question. That means it's an open-ended question where you'll get 3 marks for a good answer, 2 marks if it's reasonable, 1 if it's limited, and 0 if you don't show any knowledge of physics at all. There's no indication in the marking instructions as to what you should write here. It's really an opportunity for you to demonstrate your knowledge of physics, and a marker will take a holistic approach to marking this. In other words, they'll look at your answer and then gauge from what you have written how much of your knowledge of physics you have demonstrated. And of course that knowledge has to be relevant to the question and at an advanced higher physics level. So let's have a look at this one. It says a student finds the diagram shown in figure 7a in a textbook, and the diagram represents some of the possible electron orbits in the Bohr model of the atom. And we've to use our knowledge of physics to comment on the suitability of the diagram as a representation of electron orbits in an atom. Well, looking at the diagram, the orbit when n equals 3 seems to be showing a wavy line that's equal to 3 complete wavelengths, and then we've got 4 wavelengths for n equals 4, 5 for n equals 5, and 6 complete wavelengths when the orbit is n equals 6. So the electron orbits are shown as a whole number of de Broglie wavelengths. For example, when n equals 3, that corresponds to 3 complete wavelengths. If I trace round the path, you'll see there's 3 peaks and 3 troughs in the n equals 3 orbit, and there's 4 whole wavelengths in the n equals 4 orbit. Now if we just think about the n equals 3 orbit just now, then we can write that the circumference of that orbit, 2 pi r, is equal to 3 whole wavelengths. And also from your relationship sheet, the angular momentum of an electron in an orbit is quantized in units of nh over 2 pi, where n is equal to 1, 2, 3, 4, in other words a whole number. So if we rearrange that, then 2 pi r will be equal to nh over mv, and 2 pi r then is equal to nh over p, and h over p is equal to the de Broglie wavelength of the electron. So when n equals 3, the orbit comprises 3 de Broglie wavelengths, and this is also the case when n equals 4, n equals 5, n equals 6. Now would that get me 3 marks? I don't know, depends what the marker thinks of it. But try and put down as much relevant physics as you can at an advanced higher level, and make sure you try and include any relevant relationships as well. It's also a good idea to leave the open-ended questions until the end of the exam, and then you might have a bit of time when you can concentrate on them and put down as much information as you can. Anyway, let's move on. Question 8 in the 2022 paper was also on an introduction to quantum mechanics, and it's about de Broglie wavelength. So, to produce an image of an atom, some microscopes use particles such as electrons or neutrons, and the de Broglie wavelengths of the particles should be approximately the same magnitude as, or smaller than, the diameter of the atom being imaged. And in part A we're told, in one electron microscope, electrons have a velocity of 1.75 times 10 to the 7 meters per second, and we have to calculate the de Broglie wavelength of the electrons used. So straight to your relationship sheet, the de Broglie wavelength relationship is lambda equals h over p. That's Planck's constant, 6.63 times 10 to minus 34, divided by the momentum of the electron. So you need to go to your data sheet and look up the mass of the electron. That's 9.11 times 10 to minus 31, times the velocity we're given, 1.75 times 10 to the 7. And if you do that in your calculator, you'll get an answer of 4.16 times 10 to the minus 11 meters. In A part 2, the diameter of an atom can be measured in angstroms, and 1 angstrom is equal to 0.1 nanometers, and the diameter of a gold atom is 2.6 angstroms. And we have to explain whether electrons with a velocity of 1.75 times 10 to the 7 meters per second are suitable for imaging the gold atom. So first things first then, we better change 2.6 angstroms into nanometers. So it'll be 0.26 nanometers. That's 26 times 10 to the minus 11 meters. And the de Broglie wavelength of the electron that we calculated in part 1 was 4.16 times 10 to the minus 11 meters. Then the wavelength of the electrons is smaller than the diameter of the gold atom. And we're told that the wavelength should be approximately the same or smaller than the atom. So these electrons are suitable for imaging the atom. Pretty tricky. Okay, 8A part 2, part B. A neutron microscope uses neutrons with a velocity 3 orders of magnitude less than that of the electrons in the electron microscope. Explain fully why the neutron microscope is suitable for imaging gold atoms. Well, we could do another calculation here, using this time the mass of the neutron. And the mass of the neutron you'll get on your datasheet is 1.675 times 10 to the minus 27 kilograms. And if it's got a velocity that's 3 orders of magnitude less than the electron, and the electrons had a velocity of 1.75 times 10 to the 7, then the velocity of the neutron will be 1.75 times 10 to the 4. And if we do that calculation using h as Planck's constant, then you'll get an answer of 2.3 times 10 to the minus 11 meters. And again, that's smaller than the diameter of the gold atoms, so neutrons are suitable for imaging them. Then part B, optical microscopes use visible light, and individual atoms are too small to be viewed using an optical microscope. And we have to estimate the diameter of the smallest object that could be imaged using an optical microscope. Well, to answer this, we need to think about the smallest wavelength of visible light, and that is about 400 nanometers. In fact, if you go to your data sheet, then you'll see some wavelengths of visible spectral lines there, and the smallest wavelength you'll find for violet light is 410 nanometers, so approximately 400 nanometers there for 1 mark. That's it, a lot of marks in the 2022 paper on an introduction to quantum physics. But typically, you're always going to get asked about the de Broglie wavelength or the Heisenberg uncertainty principle. And that's it for this episode. We'll see you in the next one when we're going to look at particles from space. See you in the next one.